Hi, I am Dr. Nitisha Shrivastava from Indraprastha Engineering College in Ghaziabad. I am here to teach you the subject control system. In the previous two lectures, we had an in-depth discussion and understanding about the system and control system, its basic components. Today, in this lecture, I will be teaching you the topic block diagram reduction. We'll cover the various techniques involved in block diagram reduction, as well as we'll take up some examples so that we validate the techniques what we study. These are the topics which we'll be covering, that is block diagram, the reduction techniques first involving what are the basic elements of block diagram, then the basic connections for the block diagram algebra involving the component summing point as well as the takeoff point, and we will understand the different block diagram reduction rules. So, to start with, the first element is the summing point. The symbol here, this symbol with a plus minus or plus plus represents a summing point, and this is a block G of s, H of s, what is written here is the block, R of s is the input, and C of s is the output. Here the arrow mark indicates that the signal is now fed back to the input. So, this summing point, this symbol represents the summing point, and at particular point, if the signal is being taken out for the other blocks, then that is known as the takeoff point. This is another element of block diagram. This element also represents a takeoff point. Here we are not having any block here, that means the gain is 1. This is a summing point, this is a block, and this is a takeoff point. So, basic elements of block diagrams here, this represents a block, X of s is the input, Y of s is the output, the arrow mark indicates the direction of the signal. A summing point could have two signals, that is signal A minus signal B will be the output, and here it could be both positive, or we could have here 3 signals as well. Now, in this we can see that there is plus, plus and minus. So, therefore, the output is the work of the summing point is to do A plus B minus C. So, these are the different elements of block diagram. Now, these blocks, that is how these blocks are being reduced. As we told, a particular system could have one block or could have many subsystems in it. If the system is having many subsystems in it, and to know the overall response of the system, individual blocks are reduced and then brought to one single block, so that the overall response of the system is studied. There comes the importance of block diagram reduction, so that the overall response of the system is studied and analyzed. Now, this is known as the cascade, that is G1 of s and G2 of s. When they are connected in series, they are written as G1 of s and G2 of s. The signal X of s and the output of the first block G1 of s is Z of s, and the output of the second signal, that second block, that is G2 of s is Y of s. So, what is this Y of s overall? That means the two blocks can be written as G1 of s into G2 of s. This is the basic cascade. Now, if the blocks are in parallel, like G1 of s and G2 of s, if they are connected in parallel, then G1 of s plus G2 of s is the response. The input is X of s, whereas the response is Y of s. So, in cascade it is G1 into G2, whereas in parallel it is G1 plus G2. Now, here we are understanding what happens if there is a loop. In this, G of s is the block, that is the process, and H of s is the term H is normally reserved for the feedback path. So, h of s is a feedback path. We can see that the output signal y of s is fed back through h of s to the summing point with a negative sign. Now, this combination where h of s is in the feedback loop, the block in the feedback loop when reduced will get it as g of s divided by 1 plus g of s h of s. It should be very clear that this minus sign is here, but when you work out we get a positive sign here. So, negative feedback loop, but on combination it comes out as g of s 1 plus g of s h of s. So, this block, this E of s, normally the term E of s is reserved for the error. There is a difference in the value of the input and the output, therefore, there is an error signal. Error signal is fed back to the block. So, we are going to now understand, we understood what is a summing point, how is the summing point represented, how is a block represented, what is a takeoff point, what is a feedback loop. Now, we will look at how do we reduce, that is how to move a summing point ahead of a block. While applying the reduction techniques, we may not be able to go ahead with the position of summing point at this place. In that case, what is to be done? Now, we will understand what is the output here, the output y of s, the output of the block, output of the block, output of the block for the first case is output of the block g of s is g of s into r of s, into r of s. And what is y of s? Y of s here is g of s r of s plus x of s. So, it is expected that when the summing point is moved ahead of a block, we want now the summing point to move ahead of a block. The summing point is now moved ahead of a block. For that case, the y of s should exactly match y of s which was in the case 1, that is the case 1 first block, first figure. This in this case 2. So, let us check that if a summing point is moved ahead of a block, then we need to add a block whose value is 1 divided by g of s. The block value here, this block value to whose we are moving ahead the summing point, then we have to add a block here whose value is 1 divided by g of s. Now, let us check what is the output here. Output is r of s, output of this if you are adding r of s plus this, that is 1 divided by g of s. And what is the output of this? What comes here? What comes here is x of s upon g of s. So, this becomes x of s upon g of s. This is the output of our from here. Now, this is fed to this point. So, g of s, it is now that y of s will be this multiplied by g of s. So, what is the response now? Y of s, this is a signal which is come here, this signal is come at this point. So, what is y of s? Y of s is now r of s multiplied by g of s, r of s multiplied by g of s plus x of s. Now, we can see that in case 2, this is the case 2, y of s for this output, the output y of s for case 1 is this, and when we are moving the summing point ahead of a block, we added one block here whose value is 1 upon g of s. Now, 1 upon g of s when added gives the same results. We can check here that this y of s and this y of s is same. So, this is how if you we want to move a summing point ahead of a block, then we need to add a block here, that is 1 divided by g of s. The input to this was x of s, and that input carries on over here with an additional block in between. Now, next is if you want to move this summing point beyond a block. In this, the summing point is moved beyond a block, that is this summing point has been moved beyond this. So, let us check out what is the output here. The output, the input here is x of s, the input here is y of s. R of s plus x of s is the output, and so therefore, y of s with the position of a summing point here and with the position of block here, y of s is r of s plus x of s multiplied by g of s. So, when you are moving the summing point here, when the summing point is moved here, what happens? We have to get the same y of s here. Y of s should be r of s into g of s plus x of s into g of s. So, let us check whether we are getting the same results or not here. R of s into g of s is the output of this block now, that is the gain multiplied by the input, and here we are having the input x of s is the input, and to that we have added a block g of s. We can see that the output here is g of s x of s. This output g of s x of s is added to this. So, we can see that the output y of s is the sum of g of s r of s plus g of s x of s. This is how a summing point is moved beyond a block during the block reduction. So, this is now next let us see about the takeoff point. This takeoff point, we are moving after the block. This is the takeoff point here, and it is to be moved after the block. So, what is the output here? R of s and x of s are same. R of s is equal to x of s. Now, here the output y of s is what? It is r of s into g of s for the case 1. Now, if we move the takeoff point beyond the block, that is this, what is the output here? Output here is r of s into g of s, and we have added, since we are moving this takeoff point from this point to this after the block, we have added one block here whose value is 1 divided by g of s. So, do we expect the same, that is y of s is equal to, y of s in this case will be, the output at this point is x of s upon g of s. So, what is the output here? It is the output here is y of s should be r of s into g of s. So, r of s into g of s, that is r of s into g of s is the output. That is what been fed over here, right. This gives us the x of s value. So, this is how the output, the takeoff point is moved beyond the block. Similarly, if this takeoff point is moved ahead of the block, then we need to add g of s block here. So, these are the 4 ways how we can shift a summing point either beyond a block or ahead of a block, depending on how the reduction is to be applied. So, these are certain block diagram reduction rules. I will just look at it, what it is. Check for the blocks connected in series and simplify. So, the first step is we need to connect, see if the blocks are in cascade, then we can reduce the 2 blocks to single 1 block. Similarly, if the blocks are connected in parallel, we need to simplify. These are the 2 things we will check first, and then if there is any feedback loop, then simplify the feedback loop by the particular reduction technique. And then if there is any difficulty in simplifying with a takeoff point or a summing point, then we will shift it towards right or left, and then step by step reduce the complete different blocks into one single block. So, till the above till all the complete block is one single block is not been achieved, we continue this checking various blocks. So, now this was about the techniques involved, the different elements of block diagram. Now, this is one example of block diagram reduction. Here it can be we can see that this is the input R of S, this summing point is having plus, this summing point plus minus the blocks G1, G2, H1, and here the various blocks G3, G4, H3 and these things. Now, this has now to be reduced to a single block. This is now to be reduced with a single block, and let us see what is the transfer function of that. Transfer function is output upon input. Output is R of S and input is Y of S. We have to find out using the different reduction techniques what is the transfer function obtained Y of S upon R of S. Once we know the elements or we know the components of this, then the analysis of a particular system could be done. It could be different components or different elements of a one big system which are connected in this function to get the desired response. This is the transfer function which we need to get. Now, the first thing we need to check is there any blocks connected in cascade or is there any blocks connected in parallel, and then we will move for the other part. In this slide we can see that these two blocks G1 and G2 are connected in cascade. So, the first step in the reduction is shown here, this becomes G1 and G2. Next we can see in this block that G4 and G3 are parallel. This is a parallel combination, parallel, and this is cascade. This is the cascade combination. So, according to the steps or rules what we have studied, in that it is that first we need to check whether whether any blocks are in cascade or in parallel. In this complete combination we can see that, and that has been reduced in the next block. We can see this is parallel combination and this is the combination G1 and G2. What else to check now? Once these two blocks are reduced, there is some reduction in the number of blocks or number of components in the original block diagram. Now, we can see that one summing point from here is also not there because we have added this to G3 plus G4 and got a single block. Now, how can we add up these two things? In the next step we need to take care how do we add up. One combination what we are getting here is this, the other combination what we are getting is this. That is, we can see here in this slide this takeoff point, since we are not able to bring the two blocks in cascade, G3 plus G4 block and G5 block are not coming together just because of this takeoff point, and therefore, we can shift the takeoff point beyond a block. So, we will just see what do we do to shift a takeoff point beyond a block. To shift a takeoff point after a block, then in that case the value of the block will be, which is connected here, will be 1 divided by G of S, that is the value of block. So, here we can see that this takeoff point when moved that side. So, this block will have another block, that is H2 divided by G5, H2 divided by G5. This is a new block added here, that is 1 divided by G5 will be added, and both comes in combination as a cascade element. Therefore, H2 upon G5 will be the result. That is what has been done here. This takeoff point is moved beyond the block, and therefore, we have this combination. This is one part which had to be taken care of, and that is done. That is, the takeoff point is now moved at this with an additional block 1 divided by G5 here. And now, this was another thing, that is the feedback loop. G1 and G2 are in the forward path, whereas H1 is in the feedback path. So, we can reduce this with the combination. What was, yes, this is how, that there is a gain here and there is a feedback loop here. So, in that case, what is the combination? It is G of S divided by 1 plus G of S H of S. It is a negative sign here, and therefore, here also we can see that there is a negative sign. This is having a negative sign in the original. So, what is the result of this block? It will be, this block could be written as G1 G2 divided by 1 plus G1 G2 H1, right. So, G1 G2 upon 1 plus G1 G2 H1. So, this is also now solved, this part, and this part is now solved. So, these two blocks are in cascade, that is, we can write this in cascade, and this combination with the feedback loop H3, that is the next step. We can see that now it is G3 plus G4 is now in cascade with G5. G3 plus G4 is written in this way, that is G3 plus G4 in cascade with G5, and this was due to the takeoff point. The value of this block is now H2 by G5, and we have here a feedback loop originally in the diagram. Yes, we had a feedback loop originally in the diagram, which is after the G5 block and reaching here with a negative sign. So, here what is in the gain? The gain here is, yes, the gain here is G3 plus G4 into G5, this with the feedback loop divided by 1 plus this combination into H3. So, after this reduction, now so many blocks were available in the original figure. Now, we can see that we have used the feedback loop reduction, we have used the takeoff point moving beyond a block, as well as the combination of cascade. So, this is what comes out to be this combination, and this is again now in cascade with this block, that is G1 G2, which was here. This block and this block are in now cascade. After the feedback loop has been reduced, the summing point is now no more here. The summing point along with the combination of the feedback loop is no more here, and now these two blocks, that is G1 G2 divided by 1 plus G1 G2 H1 is in cascade with the second block G3 plus G4 into G5 divided by 1 plus G3 plus G4 into G5 into H3. So, these two blocks are now in cascade. Later we are very well understanding what would be the next step. Once the two blocks in cascade are solved, these two blocks in cascade are solved, and then we have a feedback path. In the feedback path, the value of feedback loop is H2 by G5. So, in the next step we can see that the combination of the two cascade blocks comes out to be so, and then the final reduction using the feedback loop. So, this is the overall transfer function using the different techniques. The solution, the final answer here is, this is y of s. This is the final solution. This is the final solution of the original block diagram using and now we have achieved one single block. So, the output upon input transfer function is available to us. With the help of this transfer function, we could process or analyze or design as per the requirement. Thus, we can study the response of any system by using block diagram reduction technique. One more example, let us see. I have taken up this example. Now, here in this example, what is to be understood here? This is G2 and this is G3. In G2 and G3 combination here, this block cannot be cascaded just because of the presence of this takeoff point, and this takeoff point is not allowing us to cascade G2 and G3. Now, in that case, we can move this takeoff point beyond the block. Takeoff point is to be moved, beyond block G3. So, what is the result here? What happens to this block once it has been moved to there? It becomes H1 divided by G3. H1 divided by G3 is an additional block. With the help of this, then we will be able to move the cascade. We will be able to solve the cascade G2 and G3. Then after that, what is the next step? So, in step 1 we are going to do this. This would be step 1. Once this is done, then step 2 is cascade of G2 and G3. So, once this has become one complete block, then in feedback loop we have the value H2. H2 will be in the feedback path. So, we can solve the cascade G2 G3, that comes out to be step 3. In step 3 it will be feedback loop with H2. So, once that feedback loop is solved, this part of the block diagram will be reduced. In this we will have one block. This will give us one block that in cascade with G1. This block in cascade with G1 will give us another one combination here. This will give us another block. This becomes this is step 3, and this will be step 4, where this block is in cascade with G1, and then the entire combination, this combination is in feedback. Since this takeoff point is now moved here, it is in this path. So, this entire step 4 will give us now here step 5. This step 5 is reduction of this complete block with the feedback loop H1, and after that the block is this much. We can see that the feedback path is moving. Here there is no block, that is, this feedback is fed back to the directly fed back to the input, that is, the output y of s is directly fed back to the input. Now, in this case the term is, the gain here is treated as 1, and since it is going to a minus sign, so the gain here will be minus 1. So, this becomes the final combination with the feedback loop of 1, unity feedback loop. It is termed as unity feedback loop. So, this gives us the final transfer function. Let us check out that this final transfer function, what it is. So, this is how the block G2 and G3 is cascaded after moving the takeoff point here, So, we have 3 takeoff points here, one going to this part, another to the summing point, and one to the feedback loop. So, this combination is, after this it has been treated with the feedback loop, and then this and this block in cascade, and then in the feedback loop gives us this value, and this is the final result here. The final block is this. So, the overall transfer function, that is output upon input, is this. So, once the response of once we get the transfer function of output upon input, then the system could be analyzed, or system could be the analysis in time domain or frequency domain, wherever it is required, could be done. The overall system response is now available using the block diagram reduction technique. We had seen what are the different ways how can we move the summing point and the takeoff point at or beyond a block, and we understood how do we represent a summing point where the two signals are added or subtracted, and we have also understood what is the feedback loop and how gain and the feedback path is reduced to a single term. We have taken up 2 examples. I hope these 2 examples give you a clear picture on solving more examples related to block diagram reduction. Thank you very much.